Good morning and welcome to Tech 293 on Tuesday, April 27th. Today's video is kind of a bittersweet video, at least for me, because it's the very last video in the class. So I guess it's a little bit sad because I really enjoy this course. I really enjoy teaching it. I really enjoy all the material in the course, and I definitely enjoy doing the labs in this course and breaking stuff in different ways and working with different materials. So I hope that you've had a good time in the class. I hope you've enjoyed at least doing some of the labs and breaking some stuff and seeing how different things fail. And I hope you've learned something as well. So hopefully it was kind of some combination of having a little bit of fun, but also learning something at the same time. That's the best of both worlds when you can combine those things. So it's a little bit sad, but I'm not gonna lie, I'm also happy as well. I like summer break as well as anybody else. I like doing all the things in summer, like being outside and going for bike rides and runs and being on the lake and things like that. So I'm really excited for summer break as well. So I'll miss you guys. I'll miss not being able to go in the lab and work on labs with you guys, but on to other fun things in the summer, and I'm sure you'll agree with that as well. The purpose of this video is to talk about the last exam. I don't really call it a final exam because it's not really cumulative over the entire semester. If you look in the syllabus, remember there are some things from the early part of the semester that it does cover, but it's not fully cumulative. But before we talk about that, let's take a look at the schedule. There's not much left in the schedule. Today is April 27th, and we still have Lab 9 due. Lab 9 is due on Sunday, May 2nd at 11:55 p.m. I tried to push that due date back pretty much as far as I could. Obviously, you can turn it in whenever you want to, so you don't have to wait until Sunday, May 2nd to turn it in. But that's when it's due, by 11:55 p.m. That's the last lab in the class. And then exam 3 on the schedule just says TBD because the registrar doesn't announce the schedule until halfway through the semester. But if you look on your final exam schedule, I'm not actually sure where students look to find their final exam schedule. For me, it's in a website called the Faculty Center. But I double checked, and the final exam for this class is supposed to be scheduled on Thursday, May 6th from 1 o'clock to 3 o'clock p.m. That's when the final exam is scheduled as per the registrar's office. But it's going to be an online exam like exam 1 and exam 2. In fact, the format's going to be very similar to exam 1 and exam 2. So I don't see a good reason to limit it to those 2 hours, that 2-hour window specified by the registrar. So I'm going to do it the same way that we did exam 1 and exam 2. It's going to open up at midnight at 12 o'clock a.m. on that day. So that would be Thursday, May 6th. They will open up at midnight, and then you will have a 3-hour window, but you can choose which 3-hour window on that day. So it'll open at midnight. It'll close at 11:55 p.m. on that same day, Thursday, May 6th, but you can choose any 3-hour window inside that day to take the exam. Obviously, don't wait until 11 o'clock to start the exam, because then you've reduced that 3-hour window to a one-hour window. So give yourself the full 3 hours. I don't think it'll take you the full 3 hours, but you may as well allow yourself the full 3 hours before, at the end of that 3 hours, ReggieNet will automatically submit whatever you have completed at that point in time. So that is going to be when we do exam 3, Thursday, May 6th, any 3-hour window that you want. And the purpose of today then is to talk about that exam in some more detail. So we'll talk about the content in just a couple of minutes, but first, I'll say a few words about the format. It's going to be very similar to exam 1 and exam 2. There will be some multiple choice or true-false questions, and there will be some calculation questions. I haven't set up the exam yet, so I can't tell you exactly. I don't know exactly how many questions there'll be, but probably somewhere between 50 to 60 questions, something like that. And probably about 2/3 of the points on the exam will come from the multiple choice or true false questions. And probably about 1/3 of the points on the exam will come from the calculation questions. The calculation questions, most of the calculation problems that we did in this last third of the semester come from beam bending. So we had several beam bending practice worksheets, and that was the subject of a whole day's worth of videos during the beam bending section. So I would recommend doing those again. It doesn't hurt to do those worksheets a couple of times. Make sure that you're really comfortable with them and you can do those problems pretty comfortably and pretty easily without having to go back and look at the answer key that I provided in the videos. So make sure you're really comfortable doing those beam bending practice problems. And if you are, then you can probably do the questions on the exam, no problem. So that was most of the calculation questions. There were also a couple of calculations for shear stress, and there were some calculations for impact testing, but those were not as complex as the beam bending problems. Not that the beam bending problems were super complex, but there are a few more equations and you have to know which equations to apply in which specific case. So it's worth getting some practice on those beam bending problems. All right, so with that, let's go ahead and talk about the content material for the exam in a little bit more detail. So I'm going to switch over to my slides.
All right, review of material for exam 3. First of all, remember that while exam 3 is not cumulative per se, it doesn't cover the entire semester, but it does cover a few of the first things that we talked about in the semester because they're relevant for all of the mechanical properties that we've talked about in the semester. So if you look at page 2 of the syllabus, I've got it right in front of me. It says on page 2, exam 3 covers material from items 1 and 2, which is Introduction to Materials Testing and Molecular Structure of Materials, in addition to material from items 6, 7, and 8, which is heat treatment and failure modes, flexural testing, and shear stress. So be aware that it does cover some of that molecular structure of materials material as well. All right, the format we've kind of already talked about. There will definitely be multiple choice and true false. There probably won't be any short answer this time. I'm not going to write any short answer because it's an online exam. And so I'm not going to have you type in short answers on ReggieNet. So probably won't be any short answer questions on this exam. Definitely will be some calculations. The calculations will focus on beam bending testing, as well as shear stress for the most part. Not saying there couldn't be any other calculations, but the most relevant calculations for this exam are going to be beam bending and shear stress. The emphasis is going to be on heat treatment and failure modes, which includes impact testing, and beam bending and shear stress, because those are the topics that we've talked about since exam 2. So while there still could and probably will be some material from the first 2 weeks of the semester, the emphasis will be on these topics right here. The resources that you should have available to you as you're taking the exam, there's going to be some calculation problems. So you want to make sure that you have a calculator with you. You don't want to be trying to do these calculations on manually by pen and paper. That would be not very much fun. So make sure you have a calculator. You're going to want to write these out. I would strongly recommend that you write out these calculations instead of trying to keep track of everything on your calculator and in your head. So have a piece of scratch paper and have a pencil or a writing utensil handy as well so that you can keep track of the steps that you're doing in the calculation problems. Normally on this exam, I allow students to have a notes page, but this is an online exam, so a little bit different this semester. So you're allowed to use basically any resource you want except for each other. So you can't be texting or calling or communicating with other students about this, but you can use your lab manual. In fact, I'd recommend it. You can use your labs. I would recommend those. You can even use the videos that I've made. That might be a little time consuming to be finding the relevant part of the video, but you can if you want to. I think the probably most relevant resources to have on hand are your lab manual and the calculations from the labs that you've done and the example beam bending worksheets that we went over a couple of weeks ago. All right, so to review some of the first stuff that we talked about in the class that could still appear on exam 3, we talked about 5 different types of engineering materials and some basic properties of those. And we talked about 4 different types of bonding, 3 at the atomic level, 1 at the molecular level. The 3 atomic level bonds were ionic bonds, covalent bonds, and metallic bonds. So you should know what those bonds are and some properties of materials that have those bonds in them. And then the molecular level bond we kind of generically called intermolecular or van der Waals bonds. And within that group, there's a particularly strong type called hydrogen bonds. So you should know what types of elements bond with hydrogen bonds and what are some characteristics of hydrogen bonds, as well as intermolecular bonds. We also talked about lattice structures, and we talked about how many different types of lattice structures, aka Bravais lattices, there are. The 4 that we spent the most time on were the simple cubic, the body-centered cubic, the face-centered cubic, and the hexagonal close packed. And you should know some characteristics of each type of lattice structure, and you should know the packing factor for each of these types of lattice structures. We also talked about alloys. We talked about 2 different kinds, interstitial alloys and substitutional alloys. And we gave some examples of some interstitial materials and some substitutional alloy materials as well. And we said that you could have both. You could have alloys that have both interstitial elements as well as substitutional elements. So you should know the difference between those. And we talked about grains and how they form and how grain structure, large grains, small grains, how they influence the mechanical properties of the material that they're in. And then we talked about metals. We talked about ferrous metals versus non-ferrous metals. How do you know the difference? What's the definition of ferrous versus non-ferrous metals? What are some characteristics of each type of metal? And some overall general properties of metals. All right, now we're getting into the first part of heat treatment. One of the first things that we talked about was an equilibrium diagram, aka a phase equilibrium diagram. And about the level of familiarity that I think you should have is if I gave you a blank phase equilibrium diagram for steel, you should be able to fill in the phases. Like, what do you have here? What phase do you have in this region of the equilibrium diagram? What phase do you have over here? And so on and so forth. You should be able to fill in a blank phase equilibrium diagram for steel. Some of the most relevant phases of steel are austenite and ferrite and pearlite and cementite. You should know where those go on the phase equilibrium diagram, and you should know the properties of each of these phases. You won't find martensite or bainite on a phase equilibrium diagram because they're not equilibrium phases, but you should know what they are, and you should know what their properties are and how we could get them, how martensite or bainite could form. When we start talking about heat treatment, largely it's a question of the structure of the carbon. Where is the carbon in the steel? And you should know the lattice structure of each of the steel equilibrium phases. And the reason that we have these different phases, like I said, is kind of about the carbon. Where does the carbon go? So the solubility of the carbon, the amount that a phase can absorb, the amount of carbon a phase can absorb, to a large degree determines the phase that you're going to have form and the mechanical properties of that phase. So you should know about the carbon solubility in, say, austenite versus the carbon solubility in, say, ferrite, and how they're a little bit different. Also, we had something called the eutectic point, and that eutectic point occurred at a place where the carbon percentage was right about 0.8%. So you should know how the equilibrium phases differ for steel that is less than 0.8% carbon compared to steel that is greater than 0.8% carbon. That's a pretty major dividing line on the steel phase equilibrium diagram. The next diagram that we talked about was the triple T, time temperature transformation diagram. You should know what it is and how you could use it, and that should tell you what happens when you cool down a steel specimen really quickly, what kind of phases you end up with. And the last set of processes that we talked about with regards to heat treatment were these 4 primary processes in heat treatment. They're all pretty easy. They only have a couple of steps in each one, but you should know what they are. And you should be able to describe what's going on in each one of these heat treatment processes. The first one was hardening, which, as its name implies, hardens the material at the expense of making it more brittle as well, and not as tough. Tempering is the next process. The thing you should remember for tempering is toughness. T for tempering, T for toughness. And so toughness is the main thing that tempering is trying to accomplish in a specimen. Normalizing means making all of the grains uniform and consistent in size. And so as a result of that, you make the mechanical properties more uniform in different dimensions or axes on the specimen. And then annealing, the main purpose of annealing was to increase ductility. So you should know what the steps are to anneal a specimen. The way that we tested our heat-treated specimens is by doing impact toughness. And before we talked about impact toughness procedure, we had to talk about how things fail. And so generally we can categorize things as failing either via ductile failure or via brittle failure. It's usually one or the other, and it's usually fairly clear which way a material failed. So we talked about how to identify parts. I brought out some sample specimens, and I showed you with the document cam some specimens that had failed via ductile failure and some that had failed via brittle failure. So you should be able to look at a picture and you should be able to identify, was this an example of ductile failure or was this an example of brittle failure? With regards to those two failure modes, ductile and brittle failure, they have very different mechanisms for how they occur. So you should be able to talk about and identify the mechanism by which a material fails via ductile failure, and the same thing for how a material fails via brittle failure. And with regards to these different failure modes, we also talked about some exacerbating effects, some things that could make a part fail via brittle failure, whereas it might normally be a ductile material. So there were several things that we talked about where you might have a relatively ductile material, but if you have these kind of exacerbating specific situations, then they might cause the part to fail via brittle failure, even if the material is normally ductile. So you should know some of these factors that might tend to make a specimen fail via brittle failure. One of those was temperature. And we talked about the ductile to brittle transition temperature. That is the temperature at which a material that normally fails via ductile failure will now fail via brittle failure. And so we talked about what it is and why it occurs. Remember, it's all about which takes less energy to make it happen. And we talked about specifically what kinds of materials, not all materials have this, but we talked about what kinds of materials have ductile to brittle transition temperature or are more susceptible to it. And we also talked about the effect of carbon content, because the amount of carbon in the steel does have an impact on the ductile to brittle transition temperature. Just to avoid confusion, remember we also said the DBTT is the same thing as the RTT, reference transition temperature. They're two different phrases that mean the same thing, just depending on what reference you're looking at. The way that we tested toughness is by doing impact toughness testing. That is the most common way in industry of testing the toughness of a material. And the two common types of tests are the IZOD test and the Sharpie test. You should know how these are conducted and the differences between them. They're pretty similar, but there are a few substantial differences, mainly with regards to how the specimen is held or supported. And you should be able to describe how to conduct the test. Then we move into beam bending or flexure testing. And first of all, there's some terminology that we need to discuss, or you have to be aware of before you can do the calculations. A lot of this is very similar or analogous to tensile and compression testing, but the terms are a little bit different. First of all, we have the flexural modulus, which is the material property that you can look up in a table. The moment of inertia has to do with the specific shape of the specimen, not just the cross-sectional area like we had in tension or compression testing, but the actual shape, whether it's an I-beam, how tall is the I-beam, how wide is the I-beam, the pipe, what's the wall thickness, and things like that affect the moment of inertia. So you should be able to calculate the moment of inertia for lots of different types of specimens. The flexural yield strength is analogous to the yield strength for tensile testing. It's the point at which you no longer have elastic deformation in beam bending, and you start to get plastic deformation in your beam bending test. The flexural strength or modulus of rupture, these are analogous to the ultimate tensile strength for tensile testing. It's the maximum stress that you can have in the beam before it fails. When we were talking about beam bending and testing of beams, we talked about 4 different factors that affected the amount of flexure or bending or deflection that you're going to have in a beam. One of them was the material property, the flexural modulus. That's the material property that you can look up in a table. It's E sub B, where the little b is for bending. The next one is the geometric stiffness, which is given by the moment of inertia, I. And there's this other term that we defined that usually appears like this. It appears with these together in the equations, and that is E sub B times I, which we call the flexural rigidity. So the flexural rigidity of the part is due to both the stiffness of the material property, combined with or multiplied by the geometry of the specimen given by the moment of inertia. All right, make sure you're able to calculate moment of inertia for lots of different rectangular, circular, hollow shapes, I-beams, pipes, channels, things like that. Then we talked about how the load is applied and how the beam is supported. Those are our last 2 of the 4 things that affect the amount of load a beam can support. And to discuss those, we had these different equations. So we had 4 equations for deflection or deformation in a beam. And remember, these were only valid in the elastic region of the beam. So if you're not told to assume that the stress remains in the elastic region, then the first thing you need to do is calculate the maximum stress in the beam and make sure that is below the flexural yield stress. All right, that's the first thing you should do in your calculation problems, unless you're told to assume that the stress remains in the elastic region. All right, so these are the equations for deflection in a beam. There are going to be 4 of them. 2 of those 4 are for simply supported beams, and 2 of those 4 are for cantilever beams. And for those 2 that were simply supported beams, one was for a point load applied in the middle, and one was for a uniformly distributed load along the beam, like a bookshelf. And then for the cantilever beams, once again, one of those equations for the cantilever beam was for a point load applied at the tip of the cantilever, and the other one was for the cantilever beam with a uniform load applied across the beam. So those were our 4 equations for deflection in the beam. And then we also had 4 equations for stress, the maximum stress in the beam. And once again, we had 4 of those. 2 of those were for cantilever beams, 2 were for simply supported beams. And of both of those, we had equations for point loads applied at the middle of a simply supported beam or the end tip of the cantilever beam, or uniformly applied loads across the length or span of the beam. Okay, then we did some examples where we solved these problems using these equations up here. And the best worksheet to review are going to be those 2 review worksheets for beam bending that are in your lab manual that we went over one day in class. The last thing we talked about was shear stress, and we talked about the definition of shear stress, what it is, and how it's different from, say, tensile stress or compressive stress or beam bending stress. And we calculated shear stress. The equation was really simple. It was just force divided by area, but you just have to be a little bit careful about what is the area. The area is not always the cross-sectional area. It's the area of the shear plane, the plane across which you're trying to cause that sliding motion. We talked about single shear versus double shear. We even said, oh, you could have triple shear or quadruple shear. So you should be able to identify situations where you have single or double or triple or so on shear, and you should be able to discuss the advantages of, say, double shear as opposed to single shear. And lab 9 is a shear stress lab where we test different types of adhesives, glue. And when we do that, we have different kinds of failure that could occur. So I want you to understand what cohesive failure is, what adhesive failure is, and what substrate failure is. Sometimes in some specimens you can get more than one, but you should be able to identify what these are, what it means.
Of course, the other things that we did during this portion of the class were the labs to help us apply some of the material that we talked about in class. So we did lab 7. That was the first one in this section of the class. Lab 7 was about heat treatment. Remember, we applied several different kinds of heat treatment to different metal specimens. We also got one of the specimens really, really cold, and we saw what effect all of that had on the failure modes, how the impact failure was affected. So we also learned about impact testing in the process. So lab 7, one of the reasons I kind of like it is because it kind of combines several different things. We talk about heat treatment and we see how that works and what the effect that has. We talk about impact testing, we talk about failure modes, and we talk about ductile to brittle transition temperature, low temperature effects. So it kind of combines all those things into one lab, which is why part of the reason why I like lab 7. The other reason is because I get to play with liquid nitrogen, and that's fun. So that was lab 7. Make sure you're familiar with all those concepts in lab 7. In lab 8, we talked about beam bending, and you designed your own beam. And then you did a bunch of calculations on your beam to determine when you think it's going to fail. You predicted what load it's going to support before it fails, and you predicted how much load it can support before it deflects by 0.1 inches, 0.2 inches, so on and so forth. So that's a good application of the beam bending calculations that we do in this class. And then in the last lab, lab 9, we talked about shear testing of adhesives. And so that's a good opportunity to talk about shear stress and make sure you can calculate shear stress, and to also talk about different kinds of failure: adhesive failure, cohesive failure, substrate failure, and different combinations thereof. So make sure you're comfortable with all those topics that we talked about in the labs. Let me know if you have any questions about anything before the final exam. I'm happy to clarify anything that we've talked about at any point during the semester. So let me know if anything comes up. So that's it for the semester. That actually wraps up the whole material for the whole semester. So I want to say thank you for being a good class and being patient. I know this was at times a challenging semester and a challenging academic year. Believe me, it was for all of us. So I appreciate your patience, and I appreciate you being a good class. Thanks a lot for everything this semester. I hope you have a great summer break. If you are graduating, then I hope you have a great start to your career. Make sure to come back and keep us in the loop and updated on what you're up to. We love seeing former students. If you're not graduating yet, then I look forward to seeing you back in Turner Hall in the fall. And hopefully we'll be back to a more normal experience where we'll actually see each other passing in the hallways and stuff like that. So that's it. Once again, thanks for a great semester. I hope you have a great summer break, and I'll see you around. Have a good one.